electrical engineer.
Hi, my name is Geneva Royer. I am the computer engineer. I am in charge of the research, FPGA research, and data collection research. As you can see in this diagram, this is a project description. First, customers will put their luggage on the conveyor belt. The camera will scan the luggage, and the TSA officer will control it with the FPGA microcontroller. Our motivation is to minimize the domestic and international flight time to less than 2 hours. We developed our division to lower the cost of TSA security devices.
All right, so a brief system description. Our system is broken down into 4 main components, these being the conveyor belt, which will move objects from point A to point B, our camera, which uses built-in firmware to control image processing, lighting, things of that nature, the FPGA microcontroller, which uses the tiny YOLO v3 algorithm to track identifying objects, and our monitor, which will display the FPGA output.
Some related theory, the Deep Vision software implements YOLO v3, which is a neural network architecture to identify objects. The neural network utilizes convolutional layers to improve detection accuracy. And so YOLO v3 specifically implements 53 convolutional layers for feature extraction. And on the right, you can see a breakdown of each layer, the filters, the size, and the output that each layer generates.
All right, so I'll give a brief breakdown of our hardware design and implementation. Our conveyor belt system is composed mainly of zinc-plated steel and PVC piping, making it nice and sturdy. A 12-volt motor is used to rotate the conveyor belt, allowing objects to move from point A to point B, and that motor is operated by a basic on-off light switch that you would find in any household. At the heart of our system is, or Dan, next slide. Sorry. At the heart of our system is a power supply that converts the 120 volts of AC electricity you would find on a normal wall outlet and takes that, converts it to 12 volts DC, which is needed for the components of our project. This power supply is also operated by another basic on-off switch that you would find in any household. In addition to all of this, we implemented a camera mount that sits just under 2 feet above the system, which will allow our camera an optimal field of view in order to scan and take pictures of the images, or of the objects, excuse me. Here we can see the wiring of our system. It can get a little hairy if you just try to look at it straight up, so there's a design on the right-hand side to follow. As we can see, power is coming off the wall and being sent into the power supply that is operated by a switch. Once the power supply is receiving power, this will be indicated by 3 lights that will turn on. Then this power is being sent to the FPGA, as well as another switch, which once it is turned on, it will close the circuit and send power to the motor, which will operate the conveyor belt. Here is a schematic for our power supply. The main thing we want to look at here is that our RMS voltage is 120 volts, which is what we would be getting off a wall outlet. So that is exactly what we want. And then here is the waveform for our voltages and our currents. Again, here the main thing we're looking at is the output waveform. That will be the blue line. And as we can see, it's sitting at 12 volts, which is what we want. We're taking the 120 and we're converting it to 12. When choosing our webcam, we consulted the EVNet website on the webpage for the Ultra 96 board. On the webpage, it listed 3 cameras as being compatible with the board. These 3 cameras being the Logitech C270, the C525, and the C920. We ruled out the C920 pretty much right away based on the price. It was a little too expensive for our project. So that narrowed it down to the remaining 2. From there, what we looked at was the field of view and the focus type, since the resolution is the same for both cameras. We decided to go with the C220 or the C270 because it has a fixed focus type and it has a smaller field of view. And now the testing results for our hardware. We went through 5 tests. The first one just being for the functionality of the motor connected to the conveyor belt. We tested it using a 9-volt battery and everything operated. So then we moved on. The second test was for the switch that was connected to the conveyor belt. Again, once the switch is on, the conveyor belt went. Once it was off, it wouldn't go. The third test was for the permanent power supply. We've got the power supply, hooked it up instead of just a regular battery, and then that, like I said, is the heart of our system. The fourth test introduced indicator lights for the entirety of the system. So we have lights saying when the power supply is receiving power, and then lights showing when the conveyor belt is on. And then our fifth test was for the final switch, which was for the entire circuit itself.
So the software implementation of this project, the YOLO V3 algorithm implements shape-based recognition as a foundation. And so what that means is, as we'll discuss on the next slide, this algorithm imports classes, and then those classes are identified with shapes. And then as you train the algorithm using machine learning, the shapes learn based on using color and stuff from those images that you're feeding it. And so even though you start out with a shape, it then transitions into both a shape and color-based identification, meaning contrast and stuff like that. The algorithm utilizes bounding boxes around detected objects, as you can see in the image at the bottom of the slide. It's very clear, very visible for the operator of the system in airport security, which is fundamental for something like this, where they'll be looking at hundreds of bags a day, hundreds of baggage, and can't miss a single flagged item. So that's fundamental.
The features of the software design, it's compatible with the FPGA board. It performs the object forecast. So after training the device, you should be able to detect the object of interest without assistance. It's capable of training up to 8 classes at once. The classes are adaptable, so you can import classes that you want in there, and you can also import the training as well. And we trained it to identify knives at the moment.
So the reason why we discussed YOLO V3 as a fundamental algorithm rather than going with something like TensorFlow with OpenCV, which other groups went with, is because of these classes. In the future, it'd be easy to add, say, a gun class or a bomb class and just add that to the data set rather than having to start from scratch, which is very useful in practice. So some iterations performed to develop the optimal software design. The darknet neural network architecture was modified to allow for the entire memory of the board to be utilized. This was a step that was important for using the FPGA board to its full potential, because half of the board uses generic RAM and the other half has programmable gates. And so by modifying the darknet neural network, we were able to access the programmable gate portion of the board. So that was very huge. It definitely increased our performance. A slightly downgraded version of YOLO V3 called the Tiny YOLO V3 was implemented to meet the hardware limitations of the AVNet board. As I just mentioned, the RAM portion of it was still limited, and despite implementing the programmable gate side, we still needed to reduce to the Tiny YOLO V3, which is a version that is specifically implemented and designed for boards for processors that have hardware limitations like ours. And then as a result of implementing the tiny YOLO v3 rather than YOLO v3, our live feed would be reduced from 38 frames per second to 15 frames per second. So accuracy isn't touched all that much. There is a slight dip in accuracy. However, the main impact is how many frames are being analyzed, I should say, or processed by the algorithm. And so that drops from 30 to 15. So our testing showed that after making this change, we had 98.4% accuracy. The data set that we used to test was a portion of the original data set that was used to train. So we implemented Google's Open Images database to get, I believe it was 640 images of knives. And then we did a 90-10 split between training and testing respectively. As a result, we had 64 images to train with, or to test with, I mean. And of those 64 images that we tested, one image had the knife unidentified. So that was our inaccurate test. We also did some testing with other objects, such as scissors. And that was just to see if it would falsely identify a knife and something that looks similar to a knife. And we had no false negatives. We had no issues with that at all. So that's why we didn't mention or have a visual for it. It was 100% success rate. So some changes that were made due to COVID-19. The board and the conveyor belt are not connected. That's because John Healy had to work on the board while I had to work on, or I said that backwards. John Healy was working on the conveyor belt and I had the board in my possession. And obviously we cannot meet up to integrate them. Another thing that was delayed and resulted in us not being able to fully complete the project was that the camera and the board are not connected and integrated correctly at the moment. Geneva and I were splitting the work on the board, and she was going to work on the camera while I worked on finishing up the algorithm. However, since I have the board in my possession, that really pushed that camera portion of it. And as a result, we didn't have the time we were expecting to, and the manpower expected to tackle that problem. And due to COVID-19, we were able to perform more testing, not so much in the software department, because it was 2 people worth of work being done by one individual. However, in terms of the hardware, we had a lot more time for testing to really build up the reliability and the confidence we have in our circuitry. Here's a quick cost analysis and bill of material. The total cost of the project was $203.56. However, that is not including the fact that the board was provided and the conveyor belt, portions of the conveyor belt were also provided. So in total, this would cost something around $600 to build if we're all done without any provided components. So project completion and future work. As I mentioned before, we were unable to complete the project. The camera can connect to the board. However, we are not able to feed a live stream to the algorithm. This is something we would certainly have been able to tackle with some more time, or if we were being able to work together still on campus. So COVID-19 definitely had a serious impact on that portion of the project. Things that we could do in the future is definitely improve the accuracy of division by including blurry images of knives and other hazardous objects in the future if we wanted to add them. This would include, or this would improve the detection, especially since the object would be on a conveyor belt. So there'd be some blurriness, and that would be important to factor in our training. And last, we could add some passwords and turn off the Wi-Fi's device or set it up with Ethernet, which would protect it from cyber attacks. Some technical challenge that we encountered. The first half, or I should say the first semester of Capstone, we were not actually working on the board itself. And Dr. Wang was trying to warn us about this mistake, and we were unable to push through the beginning parts quick enough to get on the board earlier. And as a result, we had a lot of unexpected delays on the board, which could have been taken into account and been less of an issue had we began working on the board earlier. Another issue we had was transferring the YOLO algorithm from the virtual machine that we had originally set it up on and tested it on to the FPGA board. This could have been avoided with some deeper initial research. This was the change from the YOLO v3 algorithm to tiny YOLO v3 algorithm. So some further research would have revealed that even though the board is or the algorithm is supported on the board and listed in the documentation. They specifically listed the tiny yellow V3. That could have definitely been a time saver had we noticed that little detail. And the last thing is the integration of the camera with the board. We could have started it earlier. We were intending to start it earlier. So once again, COVID-19 had a strong impact. Regardless, if we had gotten to the board sooner, like the first point mentioned, we would have been able to avoid this issue. And here's a demonstration of the hardware.
Yeah, so again, what you're seeing is the switch that controls the entire system, and then the switch that pertains to the conveyor belt itself. Here I will turn on the power for the system. As you see, the indicator lights go on, the monitor goes on, and then when I flick that switch, the conveyor belt will go, and there are 3 green lights back there that show that that is on as well.
Great. And so next up, we have a demonstration for the software. Like I mentioned before, we do not currently have the live feed working. However, this is a recording that we took with the camera, and then we just fed it into the algorithm as a video rather than a live stream. So there is the algorithm functioning, and we could see that it identified the knife.
Yes, for the code standards and constraints, according to the New York State's right of way and the International Radiation Protection Association of 1990, our deep vision should not emit an electrical field of 5K volts per meter and a magnetic field of exceeding 1G. For the general public, for 24-hour intervals, that refers to a work environment. And secondly, based on the standards for the airport security, it should be the camera should be able to detect objects within the dimension of 9-inch by 14-inch and by 22-inch for carry-outs. And we acknowledge that the YOLO V3 have the maximum object detection rate of 98.4 degrees. So we recommend that the TSA also practice their code of conduct and their responsibilities along with it.
And so that was our entire presentation. We spoke rather quickly to get through this in time. So if we glazed over anything that you're curious about or have any questions for us, we're more than happy to answer them. If there are no questions, thank you so much for attending, and good luck to everybody else who's still got their presentations.
Thank you.
Thank you.
Okay, so thank you. Let me stop the recording first.